first half of the lecture, we focused on linearity and what we mean by linear models. So linearity here, when we talk about linearity, we talk about linearity in parameters, so we don't mean really linearity in variables. This is one thing. The other thing is that now how to add a dummy. Sometimes you have different categories or questions that are answered by yes or no, okay? Or different, let's say, genders, male and female, and you want to see the differences, whether there's like a wage discrimination between male and female, so you want to see like any differences between two individuals in wage, between two individuals that have the same characteristic, but maybe they have different gender. So you compare males and females, so whether they would receive different wage or not. So this is the sort of dummy variable that you'd use, and again, the most important part here is how to interpret that beta, the estimated coefficient, and also, okay, to avoid adding the number. So the number of dummies they use has to be the number of group minus one. So you have to drop always one group to compare with. Okay, so this is okay now so far. We want now to turn to the tests. If you remember, we made some assumptions about the error term. Okay, you remember the 7 assumptions? Okay, we now want to look at these assumptions. If I go back to these assumptions, that was from last lecture, and we started with this in this lecture. So if you look at these are the assumptions we made about OLS, about this model. So first model is linear in parameter. We already know now what we mean by linear in parameter. Okay, one of the and I said these assumptions, if these assumptions are valid, then our OLS estimator is blue, best linear unbiased estimator, and we explain what that means. So because these are assumptions you make about something that you don't know, which is the error term, you need to test whether these assumptions are valid or not. So this lecture and the next lecture, or the rest of this lecture and the next lecture, we'll be talking about diagnostic tests, how to actually test for these assumptions, whether they are valid or not. So what I wanted to start with is a very simple assumption here, which is the assumption 6, that there is no multicollinearity. So I want to explain what that means. Okay, so next time we will probably cover 2 or 3 more assumptions and how to test for whether these assumptions are valid or not. So in the next part of the lecture, as I said, so we'll just focus on multicollinearity and what that means. So as I said, this is assumption 6. No exact linear relationship between or among x's or your independent variable. Okay, so these x's should not have linear correlation or linear relationship, okay, among any of these x's. So for example, if x2 plus 3x equal 1, that means I have perfect collinearity, because you can express one of them as a linear function of the other. So here x2 from there, so here x2 equal 1 minus 3x3. So in that case, you can't really include both variables. You can't include x3 and x2 in the same model. Okay, why? Because there's perfect collinearity between these both. So just for example, if you put like a silly example, of course, if you put income variable twice, measured in dollars and measured in cents, so it's the same variable. Okay, or here what I was talking about a minute ago, 2 minutes ago, what we call the dummy variable trap. If you included the constant, this one, and you have 2 groups, for example, and you included 2 dummies. So remember, so what is the rule of thumb we said? G minus 1, number of group minus 1, number of groups minus 1. Okay, so we have 2 gender, female and male, so I need to have 1 dummy. I have 4 seasons, I include 3 dummies. We have 12 months, I include 11 dummies. So I always drop 1. So if by mistake you included this one, the intercept, plus G, the number of groups, that's called the dummy variable trap. And that means you have perfect multicollinearity. And most softwares will actually not estimate the model. I will tell you there is a problem. And some of them, like Stata, they actually drop one variable. They choose to drop one for you, one group for you. Some others will just give you an error message. I think eViews wouldn't. Will just give you an error message, and it's not going to estimate the model because there's perfect multi-collinearity. Okay, perfect collinearity between two or more variables. Okay, so as I said, this is like a very rare case. It's not going to be like very common in practice. It's usually like a mistake, something you do by mistake, by including like by falling in a dummy variable trap, or including a variable like income measured once by dollar and then measured again by cents. So something that is done by mistake. And as I said, this is not something you will actually encounter in practice. What we see in practice actually is imperfect multicollinearity. So there's sort of correlation between the variables, but this correlation is not 1%, is not 100%, is not perfect. So it's somehow high, or to some level. So for example, in the same example here, or very similar to what we discussed in the previous slide. So I have x2 plus 3x3, but there's some sort of random term here, okay, equal 1. In that case, okay, you can express this as a linear function of this, okay, but there's some sort of random element here because it's not 100%, or the correlation is not 100% between both variables. And in that case, we have imperfect collinearity between x2 and x3. And unfortunately, this sort of multicollinearity, that's what you don't see, okay? So as I said, the first one, it's not a big problem because most software will warn you, okay, will tell you there's a problem. Some of them will not even estimate the model, okay? But in this case, you will have an estimation, and we will see now what will go wrong. So if there's imperfect multicollinearity, or multicollinearity that's not perfect, we will estimate the model and we will get estimation. And what will be the problem with this estimation? Well, your estimator will still blue, best linear unbiased estimator, but you will see, although you have high R square, which means you have a good model, refer or indicate that you have a sort of good model or K model, okay, you will have most of your coefficients are not significant. So even if you expect significant relationship between, or statistically significant relationship between two variables, or theory tells you that there should be, the price should affect the quantity demand, the income should affect consumption, okay, or education should affect how much earning or wage you receive. This is all what we learn from economic theory. And then we use data, estimate the model, and then, oh, actually, there's no relationship between these variables. So there must be something wrong. And it is likely to be because of multicollinearity, because one or two or more, of your variables are correlated. So in that case, as I said, you will see high R square, but mostly insignificant coefficient. And your coefficient, your estimated coefficient, would be very sensitive to the data. So if you change the size of your sample, you'll see massive change in your estimation. So, and that is the problem. And the case here, the problem here is that if you have two variables, two x's, or two of your independent variables that are correlated, in that sense, in that case, it's really difficult to isolate the effect of each one on y. So it's very difficult to estimate the impact of each variable separately on y. So how to test whether I have multicollinearity or not? So we agreed now that perfect collinearity is very rare. It's not going to happen very often. It's usually happen by mistake when you include, and as I said, your software might actually warn you about it, or even not estimate the model. But the problem is with imperfect collinearity, when I have some sort of correlation or high correlation between, it's not perfect correlation, but still there's correlation between two variables. So how to detect for this? There's no unique test, but there are some signs or symptoms that you can see in your estimation. We already highlighted one of them when you have a high R square, but few significant coefficients. So when you have high R square, you actually expect that you have a few or more of your coefficients to be significant or statistically significant. That means your model explains much of the variation in the dependent variable. But if it doesn't, then that means that's like a sign that you have a problem with, you might have a problem with multicollinearity. You could look at the correlation between x's, okay? and see where the problem come from, which two of your variables that are correlated. Or you could do some sort of auxiliary regression where you actually regress one of the x's, the other x's on one of the x's, that the one that you suspect it's causing the problem. Or you could look at something called the high variance inflation rate. So let's not just talk about it. Let's just see it in practice. Let's see some example of where we have collinearity or multicollinearity. I'm using data here that has, this is just a snapshot of the data. This is not all the data. So the variables I have here is education. So number of years of education. So this individual, number 1, has like 8 years of education. This one has 9, 12, etc. So this is the number of years of education. This is dummy variable, whether they live south or not. Okay, so that means 0. That means they don't live south. Female means if there's 1, that means the person is a female. If there's 0, that person is male. Experience, these are years of experience. So this person has, the first person is a female, and she has 21 years of experience. Union, whether they are member in a union or not, so it's yes or no, so 0 or 1. Wage, that's how much they receive. Age, their age. Race, occupation, sector, whether they are married or not. So they have like this data, and I think it's 540 observations, and we want to fit a model that explain differences in wage, or what factors that determine wage, believing that these are the factors that are important in determining wage. So what I did, as usual, I said, just look into your data. So these are the descriptive statistics of the data. As I said, yeah, it's about 534 observations, mean and other statistics. So what I want to fit here, we agreed that usually with wage, the log wage or the log lin model is much better than just than lin model. So we have here log wage, and I put all the other variables on the right-hand side. And, well, from theory, we understand that if you have more years of education, you should earn more. If you have more experience, you should earn more. If you older, probably should earn more again. So these are variables that can, and of course this would be different if you are a member in a union, or different to the sector, or what type of occupation you work, where you work exactly, whether you live south or north. So these are other variables that can explain wage. So when we estimate this model, these are the results. So what's the problem in these results? Is there any issue with these results? First of all, let's look at the coefficients we estimate. Most of them are not significant, or at least the education. This is one variable that we definitely expect that if you have more years of education, okay, you should earn more, okay? Or experience, look, experience is not significant, okay? It's not statistically significant. Age is not significant. Whether you are married is not really important or not, so, okay? So what is the issue here? And look at the R square. R square here is 0.32. Is this high or low? Low or high? So how much R square? So it goes from 0 to 1. So 0, that means your model explains 0 of the variation, 0% of the variation in your dependent variable. In this case is wage. If it is 1, that means your model explains 100% of this phenomena, or this variable, the variation in this variable. Okay, so 0% is very low, high percent is really, yeah. So when you have 0.3%, that means this model explains 30% of the variation in wage. Is this high or low? Are you sure? Okay, here's the thing that you should really learn about the R square. Okay, So it depends really on what sort of what sort of data you're dealing with. So you remember last time when we talked about, we have 3 types of data. So if you compare cross-sectional data, time series data, and panel data. So if you compare time series data with cross-sectional data, okay, with time series data, you would expect the R square to be really more than 80%, sometimes 90% or more, okay? With cross-section data, you actually have a large number of units in one point in time, so there's no variation over time. So actually looking across units, different units. And because there's so much heterogeneity, mean that these individuals, there's so many characteristics that you're not picking up there, it's actually 30% is really high. Okay, so in general, the R square with cross-sectional data will be much lower than what you would expect with time series data. When you have time series data, so you look at the variation over time, so actually you're picking up much of the variation, and that's why you get more than 90% in most cases when you do time series data. But because we have cross-sections here, we're actually comparing individuals, okay? So there's so many characteristics that we're not picking up. So when you look at 500 people, okay, there's so many things that can affect wages that are not there, are not in this model. And that's why, in general, with cross-section data, you might find R squared 10% and people publish in really high journals, top-ranked journals, and that's actually acceptable because we know that with individuals, different firms, different units, whatever these units are, could be firms, could be individuals, households, whatever, there's so much of their characteristics that we do not observe, and that's why it's not there, and it's very difficult to control for everything. Okay, and remember the cross-section data, we look at these individuals in one point in time. Okay, so you don't pick up the variation over time, you're actually looking at the variation across units in the same point in time, which is very difficult. There's so much of the variation you're not picking up because of that. It's just the nature of your data set. So what I want to say here is 30% is really high. Okay, because these are cross-section data. Okay, so don't just think about, okay, 30% is low because it's supposed to be 90 or 80, that would be high. It's just the nature of the data we're looking at here. This is cross-section data. If it was time series data, okay, I would definitely agree with you, this is really low for time series data, and it wouldn't be even acceptable for time series data. With time series data, you go above 90% very easily if you put any 1 or 2 variables. Sometimes even if you even like regress the variable in its value like in the previous time, like t-1, you will get 99% R square. So it's 100% acceptable and expected. But 30% in time series data is not acceptable, it's not really expected at all. But with cross-section data, again, because you look at a number of large number of individual, some data, this is only 500 or 540. In some data, you work with 20,000 individuals. You have data about 20,000 people. Do you expect to really put variables that pick up all the characteristics of these 20,000 people? No way. Okay, so it doesn't really matter how many variables you include in the model. Okay, so in all cases you will have really low, relatively low compared to time series, relatively low R square. So anyway, so this 30% is really high because we have cross-section data. Okay. Yeah. Well, panel data you actually pick both together, so it shouldn't be that low like this one. And it depends. When we talk about panel data, we'll talk about long panels when you have T is really long, and short panels when you have so it's different situations. So we'll come back to this and talk about it. I think it's week 7 or 9. Anyway, so at this point now, let's just think about cross-section data. We understand that the R square is actually what we see. 30% is really high. It's not that low at all. Okay, so that means our model should be picking like 30% of the variation in wage in our dependent variable. But in the same time, we see that most of the coefficients that we expect to be statistically significant, they are not. Okay, can you guess why? Can anyone guess why? Just look at the variables we included in the model and tell me where the problem came from. Do you expect that any of these variables are correlated with each other? Okay, how about if we calculate the correlation matrix? Let's have a look. How about the experience and age? How much is the correlation between both? It's nearly 98%. See, it's from 0 to 1. So it's very highly correlated. And this is something you would expect or not. Experience and age. Okay? So you get experience when you get older, you get more experience. So these two variables are really highly correlated. Other variables, they're not really much correlation. Okay, so this is 0.002 with education. This is 0.09 with age, etc. So it seems that these two variables are causing the problem, experience and age. So another way, so this is one way. Okay, so one way is to look at the correlation matrix between your x's, your independent variables. Remember, I didn't put all variables, by the way, just so I wouldn't be able to fit them all in the slide, in one slide. But I put the most important variable that I suspect there's correlation between them. Okay, so there's like, I don't know how many variables, there's about 10 variables here. I included in this correlation matrix only 5 variables. Okay, so you can actually try other variables as well, but these are the most important ones that actually age and experience are the main cause of the problem here, because obviously you would expect, I mean, it's normal to expect that experience is correlated with age. Is something that we would expect. So this is one way to actually check whether you have or detect for the presence of multicollinearity. Okay, so just by looking at the correlation matrix, you could also do some auxiliary regression where you regress these two variables on each other. So here I regress experience on age. Okay, and obviously it's statistically significant. And how much is R square? It's like 96. It's really high. Okay, my point here is, like, when you talk about this variable here is really correlated with experience. There's another way you could do it, which again, this one I'll show you how to obtain this, which is the variance inflation factor, how to calculate this in R. When you look at this, you will see experience. If you have this, there's no really clear-cut answer where you look in which value above which you'll have a problem, but usually most people look at anything from 10 and above. That means there's an issue of multicollinearity. So you'll see these all like 1 point something, except experience is 30.4, and this one is 31.1.8. Okay, so it's very obvious that these two variables are causing the issue of multicollinearity. So how do we deal with this? To deal with multicollinearity, how to remedy for multicollinearity. So now we saw an example, okay, that having both variables, age and experience, together in a model that explains wage actually is causing a problem, is causing multicollinearity, and that's why we see high R square, that our model should seems to perform okay, or to perform well really compared to how high the R square. It's really high in cross-section data. But at the same time, we saw that most of the variables that we'd expect to have a statistically significant impact on wage, they are not actually statistically significant. Okay, and that's again because we include these two variables in the same model. So what do we do now? So, well, you can't do much really. You need to drop one of those variables. And sometimes people ask me which variable to drop. Well, it depends really on your research question, what you're interested in. Okay. Another way to deal with, which we'll not cover in this lecture, and I'm not sure, I don't think we'll cover it in this course, but if we have time, I'm happy to look at it if people are interested in it, is the principal component analysis, where actually you put these variables together and you create like another variable which is not correlated with each other. So this is something we're not going to cover. So I'm going to look at the first solution, which is to drop one of the variables. So either age or experience. Let's drop one of these variables and see what will happen. So here the first estimation without age. So I dropped age. Let's look at education. Remember, education wasn't statistically significant. Now it is statistically significant. Experience wasn't statistically significant. Now it is statistically significant, and we still have the high R-square we had before. Okay, so if you compare this estimation where actually most of the variables are statistically significant as we would expect, if you compare this to our first estimation where the important variables that we expect them to be significant, they are not. Education is not significant, experience is not significant, age is not significant. So these all are variables that we expect to affect or to explain the change in wage is actually, or the level of wage, they actually they're not. And the main problem here comes from the fact that you have two variables, age and experience, that are collinear. Okay, so I estimated the model without age, and then I thought, okay, well, let's see how the model will behave if we drop experience instead. It was the same. Okay, everything is significant, all the variables are significant, all of them except only one, the first one. Okay, so they all are statistically significant as what economic theory tell us, and as what we would expect as well. Okay, so the main problem here was multicollinearity, was the collinearity between both variables, experience and age. So what is the problem here again? So again, just to sum up the story, so collinearity or multicollinearity means that there's no, it's one of the assumptions, assumption 6, A6, that's what we assumed about the our model. So there's no exact linear relationship between or among the x's, okay? And we said, okay, perfect multicollinearity is very rare, so you're not going to see it very often. It happened by mistake. But imperfect multicollinearity, when you have two variables that are correlated with each other, the correlation is not 100%, but they are highly correlated. And we saw here very clear the example wage and experience and age. So how to detect for multicollinearity? How to check whether you have multicollinearity or not. So the main symptom here, like the main thing that you can notice, is you have insignificant coefficients, but you have very high R square. Okay, so you have high R square and at the same time insignificant coefficient, which is something, it doesn't really make sense. Okay, so if you have high R square, you'd expect to have significant coefficients. Okay, you could look at the correlation between your x's, your independent variables, as we did, and we found that the correlation between age and experience is 98% nearly. Okay, it's very, very high. And we also calculated the variance inflation factor, and we said above 10 there's definitely a problem, from 10 and above definitely a problem, but some papers will actually consider 7 and 8 still high variance inflation factor. So again, you look at these variables and see which one is causing the problem. In our case, when you look at the variance inflation factor, it's very obvious here. These are the highest ones, the experience and age. When we drop these variables, that's the solution. Then drop one of the variables and re-estimate the model, and it seems to be working and is much better than the first estimation we got. Okay, so now we understand that was the main problem.